Welcome to the third user training video for Conjecture System Identification, a program that helps you take the data from your industrial systems and create simple models of best fit. In our previous training videos, we went through the main features of Conjecture System Identification and looked at how to use the program to build and select models for a dynamic industrial system, one with a single input and single output. We then talked about how to model nonlinear systems, that is, systems where the input changes and output changes are non-proportional. In this video, we're going to build on this knowledge and look at how to build and select models for a dynamic industrial system with multiple inputs and a single output. The system we'll be looking at is also nonlinear, so we'll look at ways to deal with this nonlinearity as well. The data for this session comes from an online system identification dataset collection called DAISY, which is run by the University K.U.Leuven in Belgium. A direct link to the DAISY webpage is given in the video description. DAISY contains a collection of datasets contributed for research into system identification, and you can use some of these datasets for practice in modeling with conjecture. Under Process Industry Systems, look for dataset 96-014, simulation data of a pH neutralization process in a stirring tank, and click on Description. The system we are using is a simulation of an industrial pH neutralization process, which combines and mixes an acid solution and a base solution in a stirring tank. The two inputs are the acid solution flow rate and the base solution flow rate, both in liters per second, while the output is the pH of the resulting product. We note that the sampling interval is 10 seconds, so each 1 on our timescale is actually 10 seconds. Once you've familiarized yourself with the system description, go back to the DAISY page and click Data to download the dataset. It comes in a zipped file, which you'll need to extract and then import the data into your spreadsheet program. You'll start with data that looks like this. So as stated in the description page, the dataset has inputs to the left of the output. We need to put the output data into column A and the data for the first input into column B. You'll start with data that looks something like this. Now, as stated in the data description page, the inputs are to the left of the output, so it's actually the first input in column A, second input in column B, and then the output in column C. We need to put the output into column A, and the data for the first input into column B, and the second input into column C, so that it's in the format that we require for conjecture. Also, you'll need to remove any column headers, so you should have only data in your file. So when you're done, your data should look something like this. Now you've got outputs in column A and inputs in column B and C. Input 1 in column B, input 2 in column C. So once again, I've plotted this data with inputs and output on the same graph. You'll be able to see this in conjecture as well once you've run a model calculation, but I like to just have a look at my data first. Following chemical principles, when the flow of acid to the tank increases, we expect that the pH of the solution in the tank would go down, and when the flow of base solution to the tank increases, we expect the pH of the solution in the tank to go up. So if we look at the plot, particularly from time point 1400 onwards, we can see this relationship. So between the acid flow in red and the pH in blue. When we increase the acid flow, the pH goes down. So you can see that relationship with the base solution flow as well if we look at the first 1000 time points or so. When the base solution increases, we get an increase in the pH of the solution. So what we get from the output data is the combined effect of the inputs. Now certainly in this case, the inputs interact with each other as well, which makes modeling more complex, but hopefully with conjecture, we can get some understanding of how each individual input may impact on the output. So let's open up conjecture from our desktop to get the main window. We're going to start by modeling this system with no transformations of the data, so as though it was a linear system. We'll start with the model setup in a similar way to how we've done before. Click Load CSV and locate your data file. So in this case, that's going to be the pH data that we've downloaded from the DAISY website and unzipped. Select that and click Open, and this loads your data into Conjecture. Click Restore to see the default settings and see what comes up in the fields below. So this is different to the defaults we had for the single input system, and so are the hypothesis equations. This entire set of hypothesis equations are all part of the one model. The first two hypothesis equations correspond to each of the two inputs, x1 and x2. The filters for these inputs are y1 and y2, and these are added together to form the single output, along with the output shift, the small a. We will be using conjecture to calculate estimates for the small a, as well as for a to d. Now you may recall that when we were modeling a system with a single input, we could add input shift values, but we kept them enclosed within the double square brackets. With multiple inputs, we can add input shift values as well, but what we will do is enclose each set of values for each input inside its own set of single square brackets. So something like this, for example, if we wanted to add a second input shift to input 1, we'd go into the first set of square brackets and just add one extra input shift separated by commas. So for example here, an input shift of 10. And you see how that adds an extra term onto the first hypothesis equation. But here let's start with the default input shifts, which give us the minimum delay for inputs 1 and 2 of 1 time interval. And in this case, that's 10 seconds. So we'll just leave that as is. Now for the filter shifts. When you have multiple inputs, conjecture will give you the default of a multiple number of filters. So in this case, that'd be 2 filters or the 2 Ys if you have the 2 inputs. So that allows for each input to affect the output differently. Alternatively, what we can do is combine these equations. So in the filter shift field, we could remove the second entry entirely, like that. So we just have the 1 inside a set of double square brackets. And you'll recognize this from the time we've modeled our single input systems, where there's only 1 filter shift. But notice how this changes your hypothesis equations. Instead of having 2 filters that need to be calculated separately, you'll just have the 1. Having 2 filters, 1 for each input, is more flexible, and it potentially lowers the error in your model, but it also adds a lot of complexity, which makes it harder to generalize your model to your system at large. We'll cover this concept of generalization further in our 4th video when we talk about cross-validation, but for now, we'll keep it simple, a model with a single filter. So we'll leave this the way we've changed it to be. You may recall from the previous video that the filter shift field also allows you to add time lags to the Ys. The default setting for conjecture is a single filter shift, which will give us a first order model. Now from experience, we find that a first order model usually gives a decent fit for a lot of the systems you're going to come across in industry. If you find that the first order models don't fit well for your system, then experiment with adding a second shift value within the square brackets, like this, separated by a comma, and notice how your hypothesis equation now changes to give you a second order model. Now I don't want to go there in this case, so let's stick with a first order model. And now for the output shift. We can leave this box checked to indicate that we want an output shift in our model. And the last thing we'll do before running the calculations is to have a quick look at the initial conditions. And now that we've changed the hypothesis equations from having 2 filter shifts to just 1, we're only going to estimate A, B, C, and small a in that order. And now we're ready to calculate. So ensure that the plot model radio button is on and then hit calculate. All right, so now we have our plot. We have the process output in blue, the model output in green, and both inputs 1 and 2. Input 1 here is in red and input 2 in cyan. We need to compare the model data with the process data. Now, even on first glance, we can tell that this doesn't look like a good fit at all. What you want to look out for here are clues that the model differs from the process in a significant way, or the differences have a sort of pattern to them. So in this case that you can see, in the first half of the sample, the model sits higher than the process, and then in the second half of the sample, the model sits lower than the process. And in this situation, we'd want to consider applying a transformation to the process data and then refitting the model. So now on to the results. You can see that Conjecture has estimated values for A, B, C, and small a. Scroll beyond the model estimates to where the gain is, and notice that there are 2 gain values. Now, given that the model is such a poor fit, these gain values aren't really reliable, but I want to point them out and give the interpretation because this is how to interpret the gain for a multiple input linear system. We've talked about the meaning of the gain for a single input system in video 1, so the gain for a multiple input system is analogous to this. The first gain value, gain 0, relates to the first input. This represents how much the pH is expected to change in response to a 1 liter per second change in the acid solution flow, if the base solution flow remains constant. Here we expect the pH to steady state to 0.215, lower than the previous pH. It's calculated as B over 1 take A and B coming from our results. And as you might expect then, the second gain value, gain 1, relates to the second input. This represents how much the pH is expected to change in response to a 1 unit change in the base solution flow, if the acid solution flow remains constant. Here we expect the pH to steady state to a level 4.95 higher than the previous pH, and that's calculated as C take 1 minus A and C coming from our results. Now again, these gain values aren't reliable because of the poor fit of the model, but this is how you would interpret the gain for a multiple input linear system if you had a good fit. The error squared for this model is nearly 4,500, and when we divide this by the number of samples, we get 2.248. So the main reason for the poor fit of our model is that pH systems are highly nonlinear. It's another classic example of a nonlinear system, similar to our air pump system from the previous video. pH is the log of the hydrogen ions in a solution, so the relationship of pH to the amount of acid or base would be logarithmic, not linear. So what we would do is try taking a log transformation of one or both inputs and then refitting the model against this data to see if we get a better fit. So first we need to apply the log transformation to our data. Open up your CSV data file in Spreadsheet Program. We'll start by taking a natural log transform of input 1, the acid flow rate. So that's in column B. So let's do the calculation in column D. And then replace those values in the second column with the log transformed values. Once our data is in the right column, we can save it as a new CSV file. Say phdata_log x1, since we've only log transformed the first input. And now we go back to the conjecture main window and load our new log transformed data. And then click Restore to get the new default model setups. Now this will be similar to that of the first model we built. We're going to keep the input shifts at the defaults, just to help us assess whether taking the log transform will by itself lead to a better model. For the filter shift, again, we're going to change it to having just one filter, like we did before. I'd rather not have the added complexity if we don't need it. So again, we have A to C to calculate. Along with the output shift, we'll leave this box checked. And then we make sure the plot model button is on and hit calculate. So we find that we still have a very poor fitting model, pretty much as bad as the first model we tried. And we still have that pattern of the model sitting above the process for half the time and below the process for the other half of the time. Now, if we looked at the results, we can see that the error squared is 4,470, not much different to before. Now, for this model, we only log transformed input 1. You may be thinking at this point that we should log transform input 2 as well, and that's exactly what we're going to do. So let's go back to the CSV file in which we log transformed the first input, and we're going to log transform the second input. Now, the data for the second input has zeros in it, which you can see if we go down the column a little bit. And a log of 0 is undefined. So to prevent this problem, we're going to add a very small number, say 10 to the power of -4. To the data values, and then log transform that. Save this as a new CSV. So let's say phdata_log x1_log x2. And back we go to the conjecture main window. We're going to load our new log transform data. Click Restore to get the new default model setups. We're going to keep the input shifts at the default, change the filter shifts to a single filter, and then leave the output shift box checked. Make sure the plot model radio button is on and hit calculate. And now we can really see the difference of having taken the log transformation of both inputs. Now this looks like a much better fitting model compared to our previous one. Let's zoom in for a closer look. We find that in general, the model is picking up the main features and patterns of the process data, which is what we want. There's still some deviation, but overall the model fit is much, much better. Now, if we look at the results, The error squared for this model is much better than any of the previous models, and this gives us a mean squared error of 0.785, so much better than the 2.248 we got previously. So using the log transformations of both inputs has improved the model fit tremendously. Once we have transformations to the data, the gain becomes difficult to interpret. However, if you have a linear system with multiple inputs, you can use the interpretation of the gain that we went through earlier when examining the first model we fitted in this session. For completeness, I've tried modeling the data with only input 2 transformed and using the original input 1 data. The fit here is still very poor and actually gives a greater error than the model using the original data. It seems like taking a log transform of both inputs is necessary to get a decent fitting model. Now you could go on trying models to see if you can improve the fit further, maybe by adding more delay to the inputs. But generally, this is the approach we would take to model a system in conjecture which has multiple inputs and that is nonlinear in nature. Remember that conjecture will store all the results from models you have built in the current session, and you can access this by going to File and then Result List. One final note. It's easy to get carried away with trying to find the best fitting model, especially if you have a complex system like this one with nonlinear properties. But the most useful models are those that are simple and easy to understand, and characterize the most important features of the real-world process. As long as your model has a decent fit, it can already make a big difference in helping you to control and understand your plant more effectively. So that's all we really need to aim for. In these videos, we've covered all the essentials of how to build and select models of your plant systems in conjecture, and we hope you found this helpful. In our fourth and final video, we'll look at some checks you can use to assess whether you have a good or poor model, and some troubleshooting tips for building models more effectively in conjecture. If you have questions or feedback, please contact us at Conjecture Data Solutions. Thank you for watching, and we hope you enjoy using Conjecture System Identification.